What if I told you that right now, as you sit completely still watching this video, you contain enough energy to power a small city for an entire year? And what if I told you that this energy has absolutely nothing to do with motion? Here's something that will completely shatter everything you think you know about reality. The most powerful form of energy in the universe doesn't move at all. In fact, motion might be the least important thing about energy. Every physics textbook you've ever read, every teacher who told you that energy is the ability to do work, every definition that tied energy to movement, they were all telling you an incomplete story. In 1905, a 26-year-old patent clerk named Albert Einstein published an equation that would change everything. E equals mc. But here's what nobody tells you about this equation. It proves that the vast majority of energy in the universe exists in a form that has absolutely nothing to do with motion. Your body right now contains about 7 yp joules of rest mass energy. That's 7 with 18 zeros after it. To put that in perspective, the atomic bomb dropped on Hiroshima released about 6.3 times yd joules. You sitting still contain energy equivalent to over 100,000 nuclear bombs, and it has nothing to do with how fast you're moving. This isn't science fiction. This is established physics that completely contradicts what most people believe about the fundamental nature of reality. Before we go any further, I need you to do something for me. If you're ready to have your mind completely blown about what energy actually is, hit that like button right now. And subscribe, because this journey is going to get increasingly wild. Also, drop a comment telling me what country you're watching from and what time it is where you are. I'm genuinely curious how far across the globe this question is reaching. Are you watching this at 3 a.m. unable to sleep because you're thinking about the nature of reality? Let me know. Let's start with what you think you know about energy. Close your eyes for a second and picture energy. What did you see? I'm willing to bet you imagined something moving. A car driving down a highway, a ball bouncing, lightning striking, water flowing, wind blowing, fire crackling. This is the trap we've all fallen into. We've been conditioned to associate energy exclusively with motion, with kinetic energy, with things happening. But here's the twist that's going to set the foundation for everything else we discuss. Motion is actually one of the least significant forms of energy in the universe. Think of it like this. Imagine you have a bank account with $1 million in it, but you only ever look at the change in your pocket. The quarters and dimes you're carrying around represent kinetic energy, the energy of motion. But that $1 million sitting in your account, untouched, represents rest mass energy. Which one is more significant? Let me give you some numbers that will make this crystal clear. A baseball thrown at 100 miles per hour, which is incredibly fast by human standards, has a kinetic energy of about 148 joules. That same baseball, sitting completely still, has a rest mass energy of about 1.3 times 1016 joules. The ratio is staggering. The energy of the motionless ball is about 88 trillion times greater than the energy of its motion at 100 miles per hour. But wait, you might be thinking, if that energy is just sitting there, does it even matter? Can we even call it energy if it's not doing anything? This is where we need to completely reframe our understanding. In 1915, mathematician Emmy Noether proved one of the most profound theorems in physics, Noether's theorem. It states that every symmetry in nature corresponds to a conservation law. Time symmetry gives us conservation of energy. This theorem tells us that energy isn't really about motion or doing work. Energy is about symmetry in the fabric of space-time itself. Here's what will blow your mind. Energy doesn't exist in the way we normally think things exist. Energy is a property of systems, a mathematical bookkeeping device that nature uses to maintain consistency. It's less like a substance and more like an accounting principle of the universe. Think of it like the balance in your bank account again. The balance isn't a physical thing you can touch. It's a number that represents a relationship between deposits and withdrawals. Similarly, energy is a number that represents how a system can evolve over time. And here's the kicker. That number exists whether things are moving or not. In 1918, physicist Max Planck, the father of quantum mechanics, discovered that energy comes in discrete packets called quanta. He found that even in systems at absolute zero temperature, where theoretically nothing should be moving, there's still energy present. This is called zero-point energy, and it exists in the quantum vacuum itself, in what we think of as empty space. The quantum vacuum is seething with energy, even though nothing is moving through it. Virtual particles pop in and out of existence constantly. This isn't speculation. We've measured it. The Casimir effect, first predicted by Dutch physicist Hendrik Casimir in 1948 and experimentally verified in 1997, proves that the vacuum contains energy. Two metal plates placed extremely close together will be pushed together by the vacuum energy between them. Let me repeat that. Empty space has energy. Space with nothing in it, nothing moving, nothing happening, contains measurable energy. Now we need to dive deeper into this rest mass energy concept, because it's going to completely change how you see the world around you. When Einstein wrote E equals mc, he wasn't just making a clever mathematical observation. He was revealing something profound about the structure of reality itself. Mass and energy are the same thing in different forms. Every particle of matter is frozen energy. Your body isn't made of matter that contains energy. Your body is energy, temporarily taking the form of matter. Here's what makes this absolutely mind-bending. The c in EMC is the speed of light, which is 299,792,458 meters per second. When you square that number, you get roughly 9 times 1016. This means that every single kilogram of mass contains 90 quadrillion joules of energy. 1 kilogram, the weight of a bag of sugar, contains energy equivalent to 21.5 megatons of TNT. But where is this energy? What is it doing? This is where we need to understand something that most people never learn. Rest mass energy isn't stored energy waiting to be released. It is the mass. The mass of an object is literally the energy of that object divided by c squared. In the 1960s and 70s, particle physicists began to understand where this mass energy actually comes from. And the answer is going to sound impossible. Most of the mass in your body doesn't come from the particles themselves. It comes from the energy binding those particles together. Take a proton. A proton is made of 3 quarks held together by gluons. If you could somehow add up the individual masses of those 3 quarks, you'd get only about 1% of the proton's total mass. The other 99% comes from the binding energy of the strong nuclear force holding those quarks together. The energy of their interaction, the energy of the force field binding them, creates mass through E equals mc. Let that sink in for a moment. 99% of your mass isn't from particles. It's from energy fields. You are mostly made of frozen force fields. And here's what's truly wild. These binding forces aren't moving. They're not doing work in the traditional sense. They're just existing, maintaining the structure of matter. The energy that makes up most of your mass is completely static, completely motionless, just holding reality together. What if I told you that in a very real sense, you are a standing wave of energy in space-time? Think of it like a whirlpool in a river. The whirlpool looks like a stable, solid thing, but it's actually a pattern in flowing water. Similarly, you are a stable pattern in energy fields. But unlike the whirlpool, the pattern that is you doesn't require motion to exist. You are a knot tied in the fabric of reality itself. This leads us to one of the most profound questions in modern physics. Why do particles have mass at all? Why does energy sometimes take the form of massive particles that resist acceleration? In 2012, scientists at CERN discovered the Higgs boson, a discovery that won Peter Higgs and Francois Englert the Nobel Prize in 2013. Higgs field permeates all of space, and particles gain mass by interacting with this field. But here's the crucial point. The Higgs field isn't moving. It's a scalar field, meaning it has the same value at every point and doesn't point in any direction. It just exists, filling space with a constant energy density. Particles moving through this field are like objects moving through molasses. The field resists their motion, and this resistance is what we experience as mass. But the field itself, the source of mass, isn't in motion. It's a static property of the universe. Let's talk about potential energy, because this is where things get really interesting. You've probably heard about gravitational potential energy. A ball held above the ground has potential energy. Drop it, and that potential energy converts to kinetic energy as it falls. But here's the question that's going to break your brain. Where is that potential energy before you drop the ball? Is it in the ball? Is it in the earth? Is it in the space between them? The answer, discovered by Einstein in his general theory of relativity published in 1915, is going to sound like science fiction. The potential energy is in the geometry of space-time itself. Gravity isn't a force pulling objects together. It's a curvature in the fabric of space-time, and that curvature represents stored energy in the geometric structure of reality. Think of it like a rubber sheet stretched taut. Place a heavy ball on it, and it creates a depression. That depression represents curved space-time. Now, if you roll a marble near that depression, it will spiral inward. Not because the ball is pulling it with an invisible force, but because the marble is following the curved geometry of the sheet. The energy isn't moving. It's not doing anything. It's simply present in the warped structure of space-time. The curvature itself is the energy. Here's where this gets absolutely wild. In general relativity, energy and space-time curvature are the same thing. The Einstein field equations directly relate the energy momentum of matter to the curvature of space-time. Energy doesn't just exist in space-time. Energy is the curvature of space-time. In 1974, Stephen Hawking made a discovery that shocked the physics community. Black holes emit radiation. This shouldn't be possible because nothing can escape a black hole's event horizon. But Hawking realized that the intense curvature of space-time at the event horizon creates particle-antiparticle pairs from the quantum vacuum energy. One particle falls into the black hole while the other escapes, making it appear as if the black hole is radiating. This Hawking radiation comes from the geometry of space-time itself, from the curvature created by the black hole's mass. The energy doesn't come from motion. It comes from the shape of reality. What if I told you that you, right now, are creating curvature in space-time? Your mass warps the geometry of the universe around you. Every atom in your body creates a tiny depression in the fabric of reality. And these depressions represent gravitational potential energy stored in space-time itself. This energy exists whether you're moving or standing perfectly still. But potential energy isn't just gravitational. Let's talk about electromagnetic potential energy, because this is going to reveal something even more profound. An electron in an atom occupies certain allowed energy levels. When it jumps from a higher energy level to a lower one, it releases a photon of light. But before it makes that jump, where is that energy? It's not kinetic energy, because the electron isn't necessarily moving faster in the higher energy state. The energy is in the electron's relationship to the electromagnetic field of the nucleus. In quantum field theory, developed primarily in the 1940s and 50s by physicists like Richard Feynman, Julian Schwinger, and Shinichiro Tominaga, we understand that particles are excitations in underlying fields. An electron is a localized excitation in the electron field. A photon is an excitation in the electromagnetic field. These fields exist everywhere, all the time, even when there are no particles present. The fields are the fundamental reality, and particles are just ripples in those fields. But here's the crucial insight. The fields themselves, in their ground state, contain energy. The potential for creating particles is energy itself. Think of it like the surface of a calm ocean. The ocean has the potential to create waves, and that potential is inherent in the ocean's existence. The ocean doesn't need to be creating waves to have that potential. Similarly, quantum fields don't need to be producing particles to contain energy. Now we need to talk about something that's going to completely reframe how you understand the stability of matter: binding energy. Why don't you fall apart? Right now, your body contains roughly 7 YY atoms. Each of those atoms has a nucleus made of protons and neutrons packed incredibly tightly together. Protons are positively charged, and positive charges repel each other with enormous force at such small distances. The electromagnetic repulsion between protons in a nucleus should rip the nucleus apart instantly, but it doesn't. Why? The answer is the strong nuclear force, and the binding energy of this force is one of the most powerful examples of motionless energy in the universe. The strong force is mediated by particles called gluons, discovered through experiments in the 1970s at SLAC, National Accelerator Laboratory. These gluons create a binding energy so powerful that it overcomes the electromagnetic repulsion between protons. But here's what's absolutely crucial. This binding energy doesn't require motion. It's a static property of the quantum chromodynamic field that holds quarks together. In fact, here's something that will blow your mind. The binding energy can be negative. When you bind 2 protons and 2 neutrons together to form a helium nucleus, the total mass of the helium nucleus is less than the sum of the individual masses of the 4 particles. The missing mass has been converted to binding energy, released when the nucleus formed. This is called the mass defect, and it's the principle behind both nuclear fusion in stars and nuclear fission in reactors. But the key point is this: the binding energy that holds nuclei together exists in a static configuration. It's not moving. It's not doing work. It's simply holding reality in a stable pattern. The universe is held together by motionless energy. Let me give you a specific example that will make this concrete. A helium-4 nucleus has a mass of 4.001506 atomic mass units. 2 protons and 2 neutrons separately have a combined mass of 4.031882 atomic mass units. The difference, 0.030376 atomic mass units, equals about 28.3 million electron volts of binding energy. That energy was released when the helium nucleus formed in the core of a star, and now it exists as a deficit in the mass. The energy is literally subtracted from the mass of the system, and it keeps the nucleus stable without any motion required. Think of it like a debt in your bank account. The negative number isn't a physical thing, but it represents a real relationship in the accounting system. Similarly, binding energy is negative, but it represents a real stability in the quantum system. Now here's where this concept extends in a way that's going to seem impossible. The entire universe might be held together by binding energy at the cosmic scale. In the 1970s and 80s, physicists developed the theory of cosmic inflation, with major contributions from Alan Guth, Andre Linde, and others. This theory suggests that the early universe underwent exponential expansion, driven by a scalar field called the inflaton field. This field had enormous potential energy, just sitting in what's called a false vacuum state. The potential energy of this field didn't require any motion. It was a property of the field's configuration in early spacetime. As the field rolled down to its true vacuum state, it released this potential energy, creating all the matter and energy in the universe. In a very real sense, everything that exists was created from the potential energy of a motionless field. We need to talk about nothing, not in a philosophical sense, but in a very literal physical sense. What is nothing? What is empty space? You might think empty space is, well, empty. No particles, no fields, nothing happening. Just void. But quantum mechanics has revealed something absolutely mind-shattering about empty space. There's no such thing as truly empty space. In 1927, Werner Heisenberg formulated the uncertainty principle, one of the foundational principles of quantum mechanics. It states that you cannot simultaneously know both the position and momentum of a particle with perfect precision. But there's another form of this principle that's even more profound: the energy-time uncertainty principle. This principle states that the uncertainty in energy times, the uncertainty in time, is always greater than Planck's constant divided by 4. What this means is absolutely wild. For very short periods of time, energy can fluctuate by enormous amounts without violating conservation of energy. The quantum vacuum uses this loophole constantly. Particle-antiparticle pairs spontaneously pop into existence from literally nothing, exist for a brief moment, and then annihilate back into nothing. These are called virtual particles, and they're not just theoretical constructs. They have measurable effects. The Casimir effect, which I mentioned earlier, is the most famous example. Hendrik Casimir predicted in 1948 that if you place two uncharged, perfectly conducting metal plates very close together in a vacuum, they will be attracted to each other. Not because of any force we usually think about, but because the quantum vacuum between the plates has less energy than the vacuum outside the plates. Here's why. The vacuum is filled with virtual photons popping in and out of existence at all possible wavelengths. Between the plates, only certain wavelengths can fit, so there are fewer virtual photons between the plates than outside. The pressure from the greater number of virtual photons outside pushes the plates together. This was experimentally verified by Steve Lamoureux in 1997, and the measurements matched the theoretical predictions with remarkable precision. Empty space, nothing, void, literally has measurable energy. What if I told you that the energy density of the quantum vacuum might be the largest number in physics? Theoretical calculations suggest that the vacuum energy density could be as high as 10,113 joules per cubic meter. That's one followed by 113 zeros. To put this in perspective, the observable universe contains about 1,086 joules total. 1 cubic meter of empty space might contain more energy than all the stars, planets, and galaxies in the observable universe combined. There's just one tiny problem. We don't observe this. If empty space really had that much energy density, the universe would have been ripped apart in the first instant of its existence. This discrepancy between theoretical prediction and observation is called the cosmological constant problem, and it's one of the biggest unsolved mysteries in physics. But here's what's crucial for our question. Whether the vacuum energy is enormous or tiny, it exists without any motion whatsoever. The quantum vacuum is the same everywhere, isotropic and homogeneous. It's not flowing, not changing, not doing anything. It simply exists with an intrinsic energy density. In 1998, two teams of astronomers, led by Saul Perlmutter, Brian Schmidt, and Adam Rees, discovered something shocking. The expansion of the universe is accelerating. This discovery won them the Nobel Prize in 2011. The most likely explanation for this acceleration is dark energy, an energy density inherent in empty space itself. Dark energy makes up about 68% of the total energy content of the universe. It's everywhere, constant, unchanging, and not associated with any particles or motion. It's simply a property of space-time itself, causing space to expand faster and faster. The universe is dominated by motionless energy. Think of it like a stretched rubber band. The tension in the rubber band represents stored energy, but the rubber band isn't moving. Similarly, space-time itself seems to have an inherent tension, an energy density that's pushing the universe apart. This energy doesn't move. It is the nature of space. Let's talk about heat, because this is where the relationship between energy and motion seems most obvious. But even here, there are profound surprises waiting. You've probably learned that temperature is the average kinetic energy of particles. Hotter things have faster moving particles. Colder things have slower moving particles. At absolute zero, minus 273.15 degrees Celsius, all motion should stop, and therefore all thermal energy should vanish, right? Wrong. Spectacularly, beautifully wrong. In 1900, Max Planck was studying black-body radiation and stumbled upon quantum mechanics accidentally. He discovered that energy is quantized, coming in discrete packets. But it was Einstein in 1907 who realized the implications for thermal energy at low temperatures. Einstein and later Dutch physicist Peter Debye in 1912 showed that even at absolute zero, atoms in a solid crystal lattice have a minimum energy called zero-point energy. The atoms must vibrate with a minimum amplitude due to the Heisenberg uncertainty principle. If the atoms were perfectly still, we would know both their position and momentum with perfect precision, violating quantum mechanics. So even at absolute zero, even when all thermal motion has been removed, there's still energy present. This zero-point energy isn't associated with motion in the classical sense. It's a purely quantum phenomenon, a consequence of the wave-like nature of matter. Here's something that will absolutely blow your mind. We can make gases colder than absolute zero. In 2013, physicists at Ludwig Maximilian University in Munich created a gas of potassium atoms with a negative absolute temperature. How is this possible? Temperature is really a measure of how energy is distributed among different states. At positive temperatures, higher energy states are less occupied than lower energy states. At infinite temperature, all states are equally occupied. At negative temperatures, higher energy states are more occupied than lower energy states. These negative temperature states are actually hotter than any positive temperature. They contain more energy than states at infinite temperature. But here's the kicker. This energy distribution doesn't require any specific motion pattern. It's about the quantum states the system occupies, about the configuration of energy levels, not about particles flying around. Let me introduce you to a concept that's going to seem paradoxical. In quantum systems, energy eigenstates are stationary states. An electron in a definite energy level in an atom isn't moving in the classical sense. Its wave function is stationary, not changing in time except for a phase factor. The electron has definite energy, but it's not zipping around the nucleus like a planet around the sun. Think of it like a standing wave on a guitar string. The string is vibrating, but the wave pattern itself is stationary. The nodes and antinodes don't move along the string. They stay in fixed positions. Similarly, an electron in an energy eigenstate has a stationary probability distribution. The energy is there, fixed and unchanging. In 1924, Sachendra Nath Bose and Albert Einstein predicted a new state of matter, now called Bose-Einstein condensate. In this state, achieved at temperatures within a few billionths of a degree above absolute zero, thousands of atoms occupy the same quantum state and behave as a single quantum entity. In 1995, Eric Cornell and Carl Wieman created the first Bose-Einstein condensate in the laboratory, work for which they won the Nobel Prize in 2001. In this state, the atoms aren't really moving individually. They've all condensed into the ground state, the lowest possible energy configuration. The condensate has energy, but it's energy without individual motion. Now we're going to explore something you encounter every single day without realizing it: chemical potential energy. And it's going to reveal something profound about how energy relates to structure rather than motion. When you burn gasoline in your car, eat food, or charge a battery, you're dealing with chemical potential energy. This is energy stored in the arrangement of atoms in molecules, in the bonds between atoms. But where exactly is this energy? And what is it doing? Consider a molecule of glucose, chalcogi. This molecule contains chemical potential energy that your cells extract through cellular respiration. The glucose molecule might be sitting completely still, not moving, not reacting, just existing. Yet it contains energy that can be released. This energy is in the electromagnetic bonds between atoms. In 1927, physicists Walter Heitler and Fritz London used the new quantum mechanics to explain the hydrogen molecule, showing that chemical bonds arise from the quantum mechanical sharing of electrons between atoms. When two hydrogen atoms bond to form He, the electrons occupy molecular orbitals that encompass both atoms. The electrons in the bonding orbital have lower energy than they would in separate atoms. This energy difference is the bond energy, and it's released when the bond forms. But here's what's crucial. This bond energy isn't kinetic. The electrons in the bonding orbital are in a stationary quantum state. They have definite energy, but they're not moving in the classical sense. The energy is in the configuration, in the quantum mechanical arrangement of the electron wave function. Think of it like pieces of a jigsaw puzzle. When two pieces fit together perfectly, they're in a lower energy state, and when they're separated, even though neither piece is moving, the potential to release energy is in their spatial relationship, not in any motion. What if I told you that every molecule in your body is held together by quantum mechanical wave interference patterns, and that the stability of these patterns represents frozen energy? Your DNA molecule, the blueprint of your existence, is held together by hydrogen bonds between base pairs. These bonds have energy of about 2 to 4 kilocalories per mole, much weaker than covalent bonds, but crucial for life. This energy exists in the electromagnetic interaction between the molecules, in the quantum states of shared electrons. The double helix isn't spinning, isn't oscillating at room temperature. There are thermal vibrations, but these are separate from the binding energy. It's simply sitting there, a stable configuration of atoms held in place by electromagnetic energy that isn't going anywhere or doing anything except maintaining structure. In photosynthesis, plants capture light energy and store it as chemical potential energy in glucose molecules. The chlorophyll molecule absorbs a photon, exciting an electron to a higher energy state. Through a complex series of reactions, this excitation energy gets stored in the chemical bonds of glucose. But once stored, this energy can remain in the glucose molecule indefinitely without any motion. A potato grown 10 years ago still contains chemical potential energy from sunlight that fell on leaves a decade ago. That energy has been sitting, motionless, in molecular structure for all that time. Here's something that's going to seem impossible. We can calculate the energy content of any molecule without ever seeing it move or react. Using quantum chemistry, we can compute the energy levels of molecular orbitals purely from the Schrödinger equation. The energy is a mathematical property of the quantum wave function, existing whether we observe motion or not. In 1998, Walter Kohn won the Nobel Prize in Chemistry for developing density functional theory, a method to calculate molecular energies and structures with remarkable accuracy. This theory treats the electron density as the fundamental variable, and from this density alone, we can determine the energy of the system. The energy exists in the mathematical description of the system, in the wave function, in the probability density, not necessarily in any observable motion. We need to go deeper. Everything we've discussed so far has been building to this. Energy might not be a thing at all. Energy might be a shadow, a projection of something even more fundamental into our four-dimensional spacetime. In special relativity, Einstein showed that energy and momentum aren't separate quantities. They're components of a four-dimensional vector called the energy-momentum 4 vector. In three-dimensional space, we think of energy and momentum as different things, but in four-dimensional spacetime, they're the same thing viewed from different angles. Think of it like a shadow. Imagine a rod in three-dimensional space, casting a shadow on a two-dimensional wall. Depending on the angle of the rod, the shadow changes length. The shadow isn't the real thing. It's a projection of the three-dimensional rod onto the two-dimensional wall. Similarly, energy and momentum are projections of the four-momentum vector onto different axes of spacetime. What we call rest mass energy is the component of this 4 vector that's perpendicular to space, pointing purely in the time direction. Here's what's going to break your brain. In special relativity, Different observers moving at different speeds will disagree about how much energy an object has. Energy isn't an absolute quantity. It's frame-dependent. But all observers will agree on the magnitude of the four-momentum vector. This magnitude is the rest mass, and it's the only invariant absolute quantity. So in a very real sense, rest mass is more fundamental than energy. Energy is how rest mass appears to observers moving through space-time. In 1907, Hermann Minkowski, Einstein's former mathematics professor, reformulated special relativity geometrically, introducing what we now call Minkowski space-time. In this formulation, reality is a four-dimensional geometric structure, and motion through space is actually rotation in space-time. When you accelerate, you're not just moving faster through space. You're rotating your trajectory through space-time, changing the angle between your world line and the time axis. This rotation changes how much of your four-momentum appears as energy versus momentum. But the four-momentum vector itself doesn't change. The underlying geometric object is constant. Only its appearance to different observers changes. What if I told you that motion through space and flow through time are the same phenomenon? That when you sit still, you're actually moving through time at the speed of light? This is literally true in relativity. The magnitude of your velocity is always c, the speed of light. When you're at rest in space, all of that velocity is directed through time. As you move through space, some of that velocity gets redirected from the time direction to spatial directions. But the total magnitude remains constant. Your motion through space-time is always at light speed. Always. This motion requires no energy. It's simply the geometric nature of existing in space-time. In general relativity, energy becomes even more mysterious. The Einstein field equations relate the curvature of space-time to the energy-momentum tensor. But in this framework, it's not clear how to define the total energy of the universe. You can define the energy density at any point, but integrating to get a total energy is problematic because space-time itself is curved. Some solutions to Einstein's equations, like the Friedmann-Lemaître-Robertson-Walker metric, describing the expanding universe, don't have a well-defined total energy. The energy of the matter in radiation is balanced by the negative gravitational potential energy of the curved space-time, potentially summing to zero. The universe might have zero total energy. Here's where we're going to venture into territory that's going to seem like philosophy, but is actually cutting-edge physics: the relationship between information and energy. In 1961, physicist Rolf Landauer discovered something profound. Information is physical. Erasing information, Landauer showed, requires energy. Specifically, erasing one bit of information requires at least K_BT lane, 2 joules of energy, where K_B is Boltzmann's constant and T is temperature. This is called Landauer's principle, and it was experimentally verified in 2012 by physicists at École Normale Supérieure in Paris. They showed that erasing a bit stored in a nanoscale magnetic system dissipates exactly the amount of energy Landauer predicted. But here's what's absolutely wild about this. Information can exist without any motion. A bit stored in the magnetization of a particle, or in the quantum state of an atom, or in the structure of a molecule, is completely static. Yet changing this information requires energy. This suggests that energy and information are deeply connected, perhaps two aspects of the same underlying reality. Think of it like a book on a shelf. The book contains information in the arrangement of ink molecules on pages. This information exists without any motion. The book isn't doing anything. But to change the information, to erase words and write new ones, requires energy. In 2019, physicists began exploring the concept of quantum information energy. They found that quantum entanglement, a correlation between quantum systems that can exist across arbitrary distances, contains energy that can be extracted and used to do work. Two particles can be entangled such that measuring one instantly affects the other, regardless of the distance between them. This entanglement is a form of quantum information, and remarkably, it carries energy that can be extracted through a process called quantum teleportation. The energy exists in the correlation, in the information content of the joint quantum state, not in any motion of the individual particles. What if I told you that the fundamental reality might be information, and that energy is simply a measure of how much information a system contains? This idea, explored by physicist John Wheeler under the slogan "It from Bit," suggests that physical reality emerges from information. Every particle, every force, every interaction is fundamentally informational, and what we call energy is just the capacity of a system to store and process information. In black hole thermodynamics, developed by Jacob Bekenstein and Stephen Hawking in the 1970s, the entropy of a black hole is proportional to its surface area. Entropy measures information content, and this suggests that all the information about what fell into a black hole is somehow stored on its two-dimensional event horizon. This leads to the holographic principle, proposed by Gerard T. Hooft and Leonard Susskind in the 1990s. This principle states that all the information in a three-dimensional region of space can be encoded on its two-dimensional boundary. The three-dimensional reality we experience might be a holographic projection of information encoded on a distant two-dimensional surface. If this is true, then energy in 3 dimensions is a projection of information in 2 dimensions. The energy doesn't really exist as a separate thing. It's how information appears when projected into an extra dimension. Now we're going to explore something controversial, something that sits at the boundary of science and philosophy. Does consciousness require energy? And if so, what kind of energy? Your brain uses about 20 watts of power, about the same as a dim light bulb. This energy comes from glucose metabolism, from chemical potential energy converted through cellular respiration into ATP. But here's the question that's going to haunt you. Is this energy generating consciousness? Or is consciousness something else entirely? In 1994, physicist Roger Penrose and anesthesiologist Stuart Hameroff proposed the orchestrated objective reduction theory, suggesting that consciousness arises from quantum processes in microtubules within neurons. According to this theory, consciousness isn't a product of classical neural activity, but rather a quantum phenomenon. If consciousness is quantum, then the energy associated with it isn't kinetic energy of particles moving through neurons. It's quantum energy of superpositions and entanglements, of states that exist in multiple configurations simultaneously until observed. Think of it like a quantum computer. A classical computer stores information in bits that are either 0 or 1, and processing this information requires moving electrical charges through circuits, requiring energy proportional to the number of operations. But a quantum computer stores information in qubits that can be in superposition of 0 and 1 simultaneously. The energy required isn't for moving particles, but for maintaining quantum coherence, for keeping the system isolated from environmental noise that would collapse the superposition. What if consciousness operates similarly? What if the energy your brain uses isn't primarily for firing neurons, but for maintaining quantum coherence across large-scale neural structures? This remains highly speculative, and most neuroscientists are skeptical of quantum consciousness theories. But here's what's undeniable. Consciousness involves energy in ways we don't fully understand. When you have a thought, neurons fire, consuming ATP and releasing heat. But the thought itself, the subjective experience, the qualia of consciousness, doesn't seem to be reducible to this energy expenditure. The energy is necessary, but it doesn't seem sufficient to explain the phenomenon. Here's something that will really twist your mind. Some philosophers argue that consciousness might be fundamental, a basic feature of reality, like mass or charge. If this panpsychist view is correct, then consciousness might have an associated energy, a field that permeates space, just as electromagnetic fields do. This isn't mainstream physics, but it highlights how little we understand about the relationship between subjective experience and physical energy. In 2020, researchers using fMRI scans showed that different conscious states, different thoughts and experiences, correspond to different energy patterns in the brain. The default mode network, active when you're at rest and not focused on the external world, has a characteristic energy signature different from task-positive networks. These signatures are measurable, physical, but they don't capture what it's like to have the experience. The energy tells us what's happening in the brain, but not why there's something it's like to be you. We need to talk about one of the most fundamental principles in physics, a principle that's going to turn out to be more subtle and strange than you ever imagined: the conservation of energy. You've been taught that energy cannot be created or destroyed, only transformed. This is one of the bedrock principles of physics, derived from Noether's theorem, which states that conservation of energy follows from time translation symmetry, the fact that the laws of physics are the same today as they were yesterday. But here's what's going to blow your mind. In an expanding universe, energy is not conserved. When a photon travels through expanding space, it gets redshifted. Its wavelength stretches as space expands, and its frequency decreases. But the energy of a photon is proportional to its frequency. E equals hf, where h is Planck's constant. So as the photon's frequency decreases, its energy decreases. Where does this energy go? Nowhere, it just disappears. The universe is creating less energy as it expands. Cosmologist Sean Carroll has written extensively about this. In general relativity, energy conservation is a local law, not a global law. Energy is conserved in small regions of space-time where we can ignore curvature, but across the entire expanding universe, total energy is not conserved. This happens because space-time itself is changing. Time translation symmetry is broken in an expanding universe because the universe looks different at different times. The universe is expanding, cooling, evolving. Since time translation symmetry is broken, Noether's theorem tells us that energy doesn't have to be conserved globally. The universe is destroying energy constantly, and this is perfectly consistent with the laws of physics. Think of it like money in an economy with inflation. If you hold cash, its value decreases over time, even though the number of bills you have stays the same. Similarly, the photons in the universe maintain their identity, but lose energy as space expands. But here's where things get even stranger. In the early universe, during cosmic inflation, the inflattened field had enormous potential energy. As this field rolled down to its minimum, it released its potential energy, creating all the particles and radiation in the universe. Where did this energy come from originally? In some models of inflation, the total energy of the universe, including the negative gravitational potential energy, is exactly zero. The universe created all its positive energy from quantum fluctuations in the vacuum, balanced by negative gravitational energy in space-time curvature. The universe might have literally created itself from nothing, with zero total energy, and this might not violate any conservation laws. In quantum mechanics, we have another violation of classical energy conservation: virtual particles. The quantum vacuum constantly creates particle-antiparticle pairs that exist for time so short that the energy-time uncertainty principle allows them to borrow energy from the vacuum. These particles are real in the sense that they have measurable effects. They contribute to the Casimir effect, to the Lamb shift in atomic spectra, to the anomalous magnetic moment of the electron. All of these effects have been measured with extraordinary precision, confirming the reality of virtual particles. But virtual particles violate energy conservation temporarily. They borrow energy from the vacuum, exist for a brief moment, and then pay it back when they annihilate. Energy is conserved on average, over longer timescales, but not at every instant. What if I told you that you might be made of virtual particles? According to quantum field theory, there's no fundamental difference between real and virtual particles. Both are excitations of quantum fields. A virtual particle can become real if it absorbs enough energy before it's supposed to annihilate, and a real particle can become virtual by emitting its energy. The distinction between real and virtual is about energy and momentum conservation, not about fundamental existence. In a very real sense, all particles are fluctuations in quantum fields, and the energy they carry is borrowed from the field itself. Now I need you to really absorb what we've been discussing, because it changes everything about how you should see yourself and your place in reality. Right now, as you watch this, you are a temporary configuration of energy fields. The matter in your body is frozen electromagnetic, strong nuclear, and weak nuclear force fields. 99% of your mass comes from the binding energy holding quarks together in protons and neutrons. You are almost entirely made of energy that isn't moving. The electrons in your body are excitations in the electron field, a field that permeates all of space. The quarks in your protons and neutrons are excitations in the quark field. You are not a collection of tiny particles. You are a pattern of excitations in fundamental quantum fields that span the universe. Think of it like waves on an ocean. Each wave looks separate, distinct, but all waves are the same water, the same ocean, just temporarily formed into a particular shape. You are a wave in the cosmic ocean of quantum fields. The energy that makes you isn't yours. It's the universe's, temporarily arranged in the pattern called you. But here's what's beautiful. This pattern persists. Despite constantly exchanging atoms with your environment, eating food, breathing air, shedding skin cells, you remain you. The pattern has a continuity that transcends the individual particles. Your identity is informational, structural, not material. Every 7 to 10 years, almost every atom in your body has been replaced. The carbon, oxygen, hydrogen, nitrogen that make you now weren't part of you a decade ago, yet you persist. The energy configuration that is you maintains itself by constantly rebuilding itself from new materials. You are a self-sustaining pattern of energy, a dissipative structure maintaining far from equilibrium order by consuming low-entropy energy and excreting high-entropy waste. Physicist Erwin Schrödinger described life this way in his 1944 book, What is Life? You feed on negative entropy, on order, maintaining your improbable existence in an increasing entropic universe. And here's what's truly profound. The energy that powers your thoughts, your emotions, your consciousness, came from the sun. Photons from nuclear fusion traveled 93 million miles, were captured by plants through photosynthesis, converted to chemical potential energy in food molecules, consumed by you, and now drive the electrochemical processes in your neurons. You are powered by starlight, by the nuclear binding energy of hydrogen atoms fusing into helium in the solar core. When you think, you're using energy that was mass in the sun 8 minutes ago. You are literally made of stars thinking about themselves. But even more than that, the atoms in your body were forged in previous generations of stars. The carbon, nitrogen, oxygen in your body were created in the fusion reactors at the cores of massive stars that exploded as supernova billions of years ago. The iron in your blood was created in supernova explosions. You are stardust, reconstituted, complex enough to contemplate the stars themselves. What does this mean for how you should live? If you're a temporary pattern in energy fields, if your existence is fundamentally informational rather than material, what matters? The pattern matters. The information matters. The complexity and organization matter. You are the universe organizing itself into configurations complex enough to understand itself. Every thought you have, every connection you make, every moment of consciousness is the universe experiencing itself subjectively. Astronomer Carl Sagan famously said, "We are a way for the cosmos to know itself." This isn't poetry, it's physics. You are the mechanism by which the universe becomes self-aware. And the energy that enables this doesn't need to be in motion. The rest mass energy of your particles, the binding energy of your molecules, the potential energy stored in your neural configurations, all of this exists in relatively stable, static forms. Motion is secondary. Structure is primary. Your significance isn't in what you do, how fast you move, how much you accomplish. Your significance is in what you are. A pattern of organized energy, a local decrease in entropy, an eddy in the thermodynamic flow from order to disorder. We've come to the end of our journey, and I need to tell you something that's going to reframe everything we've discussed. Energy might not exist at all. Let me explain what I mean. Throughout this video, we've been talking about energy as if it's a thing, a substance, something that objects possess. But energy is actually a mathematical property of physical systems, a number that we calculate based on the state of a system. Think back to Noether's theorem. Conservation of energy arises from time translation symmetry. Energy is conserved because the laws of physics don't change over time. Energy isn't a thing that exists independently. It's a mathematical consequence of symmetry. What we call energy is really just a bookkeeping device, a number that helps us track how systems evolve. It's incredibly useful, perhaps the most useful concept in all of physics, but it's not a substance or entity in itself. Philosopher of science, Nancy Cartwright, has argued that scientific concepts like energy are more like tools than truths. They're useful fictions that help us organize and predict phenomena, but they shouldn't be confused with underlying reality. So what is underlying reality? According to quantum field theory, the most fundamental description of reality we have, everything is fields. The electron field, the quark field, the electromagnetic field, the Higgs field. These fields exist everywhere, always, and particles are just excitations in these fields. Energy is a property of these field configurations. A high-energy configuration is one where the field is highly excited. A low-energy configuration is one where the field is closer to its ground state. But the energy itself isn't a separate thing. It's just a number describing the field state. And here's the ultimate twist. Even the fields might not be fundamentally real. String theory suggests that what we think of as particles and fields are actually vibrations of tiny one-dimensional strings. Loop quantum gravity suggests that space-time itself is quantized, made of discrete chunks. Some interpretations of quantum mechanics, like the many-worlds interpretation proposed by Hugh Everett in 1957, suggest that reality is fundamentally a wave function, a mathematical object in an abstract Hilbert space, and everything we observe is this wave function evolving according to the Schrödinger equation. If reality is fundamentally mathematical, then energy is a mathematical property of mathematical objects. It exists in the same sense that the number 5 exists or the concept of a circle exists. It's real in its consequences and applications, but it's not a physical substance. What if I told you that the question, does energy exist without motion, might be the wrong question? The right question might be, what do we mean by existence? Philosophers have debated the nature of existence for thousands of years. Plato argued that abstract forms are more real than physical objects. Modern mathematical Platonists argue that mathematical objects exist independently of the physical world. Physical realists argue that only measurable, physical quantities truly exist. Where does energy fit in this spectrum? It's measurable and has physical consequences, so it's real in that sense. But it's also abstract, a mathematical concept that can't be directly observed, only inferred from its effects. Energy is perhaps the perfect example of something that's both real and abstract, both physical and mathematical, both concrete in its effects and ethereal in its nature. And returning to our original question, does energy exist without motion? We've seen that rest mass energy, potential energy, binding energy, vacuum energy, and quantum field energy all exist independently of motion. The vast majority of energy in the universe isn't kinetic. It's static, structural, bound up in configurations and relationships rather than in movement. Motion is actually a way of transforming energy from one form to another, of redistributing it. But motion isn't what energy is. Energy is more fundamental than motion. Energy is the capacity for change, the potential for evolution, the mathematical quantity that must be conserved due to time symmetry. You don't need motion to have energy. You need structure, configuration, relationships. You need quantum fields in excited states. You need mass-curving spacetime. You need electrons in molecular orbitals. You need information encoded in physical states. Energy exists in the architecture of reality itself. So where does this leave us? What should you take away from these 160 minutes of exploration? First, you are far more extraordinary than you realize. The energy in your body, right now, sitting still, is equivalent to millions of nuclear bombs. You are a walking powerhouse of frozen force fields. Second, reality is far stranger than common sense suggests. The universe is dominated by energy that doesn't move. Space itself has energy. The vacuum seethes with particles popping in and out of existence. Consciousness might involve quantum effects we're only beginning to understand. Third, motion is overrated. We live in a culture that prizes action, activity, constant doing. But the deepest forms of energy don't involve motion at all. Sometimes the most powerful thing you can do is simply exist, maintaining your structure, preserving your pattern against the entropic tide. Fourth, everything is connected. You're made of quantum fields that extend throughout the universe. The energy that powers your thoughts came from stars. The atoms in your body will eventually return to the cosmos and become part of other structures. You're not separate from the universe. You're a temporary eddy in its flow. Fifth, the question, does energy exist without motion, has led us to the deepest mysteries of physics, from quantum mechanics to general relativity to the nature of consciousness. Following our curiosity, asking fundamental questions leads to profound insights. I want you to do something for me. Before you click away, sit still for just 10 seconds. Close your eyes if you want. Feel the weight of your body. That weight is mass, and mass is frozen energy. 90 quadrillion joules per kilogram of you. You are a supernova's worth of energy, compressed into human form, stable, unmoving, existing. You are the universe's way of knowing itself. You are starlight become conscious. You are energy thinking about energy. If this video has changed how you see yourself in reality, share it, pass it forward. Help others discover their own cosmic significance. And never stop asking questions. Never stop wondering. Never stop seeking to understand the deep nature of reality. Because every question leads to revelations, and every revelation shows us that the universe is far more beautiful, far stranger, and far more meaningful than we ever imagined. Thank you for taking this journey with me. Until next time, remember, you don't need to move to matter. You already contain all the energy you need. You exist. That's enough.